Let's now go over how to actually use the formal method of binomial theorem. Now before we looked at the Pascal's triangle method, but I'd just like to show you the formal one. So this one right here, I will do it in black here. So we'll say, in general, if we have a plus b to the power of n, it goes like this. It's first it's a to the power of n plus, now we've learned what this here is, n1. That means a number of ways of choosing n objects taken one at a time, or n choose one, times a to the power of, in this case, n minus 1, all that times b. Now the trick is this, what I like to think about is this one right here. This is because r equals 1. So you notice this right here, and this right here, and this right here. There's actually a little stealth 1 right here. So this is sort of, there's a lot of r's going on here. So this is this, r is 1. The next term then, well, you sort of keep going, it keeps going in general, and this is the general one, so this is sort of the middle one. They all go like this. It goes nr, a to the power of n minus r, and all that is times b to the power of r. So in this case right here, you have, well, you don't know what r is. In this case, r is r. I mean, that doesn't really make much sense, I guess, but in this case right here, you look at this. So that the thing you want to look for is what r is. So this is an r, this is r, and this is r. You might wonder, what in the world does r represent? It's just a counter. It's just sort of a way to count. So you start off with sort of r is 0, then you go r is 1, then you go r is 2, r is 3, r is 4. In general, whenever you have an r, you do this. Basically, just keep going until you have something like this. Then you just get b to the power of n. In that case right there, that happens because this one right here, you have r equals n. In other words, you stop when you get here. So this starts off as a to the n, and here you finish with b to the n. So when r is the sort of nth thing. That may seem confusing, so that's why what I'd like to do then is show you how to actually use this. So we'll do this with a real example here, and maybe what I'll do is I'll actually bring this thing right here in. I'll actually copy this right here. So I'll just do Control C. Over here, I'll do paste. There we go. Now it may look ugly, so I better grab it all. Oops. Maybe I'll do it. I don't know if I can get it to sort of give it to me over here. Yeah, there we go. This is sort of what I'm going to attempt to use. I'm going to attempt to use this sort of method here. So how do I actually do that? How do I sort of use this way? Because by the way, that is what the binomial theorem is. This is it. This is sort of how it works here. So forget about the little r's that I put in, but this is the theorem here. This is how it actually works for anything. So what I would like to do then is show you how to do it with this one. So a plus b to the power of 3. So if we do that, a plus b to the power of 3. That would be, well, a to the n. In this case, n is 3, isn't it? We want this. So in this case right here, it's a to the power of 3 plus, in this case we have n, so n is always 3 here. So 3, and then we go 1 times a to the power of, in this case, 3 minus 1 times b to the power of 1. So this is where r is 1 in this case. Then we keep going. So the next term is going to be 3, 2. And the way this goes, this is a to the power of, and it's always n minus r. So in this case it's 3 minus 2, because in this case r is 2 here, times b to the power of 2. See, the way it's sort of working right now, we have r equals 1. So you notice that's why we have r is 1 here. Here we have r equals 2. So we have a 2 here, a 2 here, and a 2 here. And we basically just keep going until we reach the final thing here. So we go 3, 3. It turns out that's when you're done. And that's because you get this right here times a to the power of, in this case, 3 minus 3. All that times b to the power of 3. Because that's what r is. So in this case right here, you have sort of that r is equal to 3. So I don't know if that made any sense. In this case, technically r equals 0. You have the 0th term here. So what's really happening is this 3 here is that 3, which is that 3 there. That's sort of how they're all working. Then it's just a matter of figuring it all out. So we can say then that, well, a cubed just is a cubed. 3, 1. This is just a matter of actually calculating this. So you can do this on your calculator. And it turns out, so you can do it like this and calculate what 3, 1 is. So 3, and then you would do math. You choose NCR. That's what this is. and put in a 1. That gives you the answer of 3. So you do that and say, so it's plus 3 times a to the power of 3 minus 1, which is a squared, times b to the power of 1 is just b, plus 3, 2. So in the same way, you can do the same thing here. In this case, go, maybe I'll do entry. So that'll just give me like the last thing I did, except I will go over here and make this a 2 instead. And then I get an answer of 3 again. So I would say, so plus 3 times a to the power of 3 minus 2. Well, 3 minus 2 is just 1. So it's a, and this is b squared, so b squared. Plus 3 here I need to do. So this is 3 NCR 3. So again, we do entry, go back here and change this to a 3. It gives me a 1. So I would say, great, that means a plus 1 times a to the 3 minus 3. And that gives me a to the power of 0 times b to the power of 3. But anything to the power of 0 is just 1. That means it just gives me this. And this is my answer then. This is how I do this expansion. So it may have seemed a little bit complicated. In fact, some students really don't like using this method, but the reason why this one is really handy is, what if you had this thing to the power of 10? That might be really annoying to figure out Pascal's triangle first, but this way is actually pretty fast, because you just go 10, 1, 10, 2, 10, 3, 10, 4, 10, 5, 10, 6, 10, 7, 10, 8, 10, 9, 10, 10. Then you know you're done. That's sort of how this works. Technically, what's going on right here, there's actually a 3, 0 in front here. But 3, 0 is just a 1. So that's sort of what's going on here. That's how you can you can use this method. This is the real binomial expansion in order to expand something like this. Now we've seen this in a few different ways. We've done this expansion here by hand. We've done it using the Pascal's triangle method, and now I've just done it using the formal method. Now what I personally like, I like a combination of the two methods. In other words, what I usually like to do is I say, forget Pascal's triangle. What I'll do is let's say I expand this. What I would start by doing is first saying, all right, if this is to the 4th, then I know it's going to go like this. These things are going to go 4, 0. And I know I'm going to have, blank, 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 blank like this. Plus, and then I would go 4, 1. In other words, see, these I'm using from the binomial theorem. These notation here, these are the number of combinations of choosing 4 things taken 0 at a time, or 4 things taken 1 at a time. So there I'm using these combinations. And then I would say plus, and then I would keep going. So 4, 2, bracket, 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 plus 4, 3, bracket, 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 bracket. Maybe I need some more space here, so I'm going to drag this whole thing over this way here. Seems I'm running a little bit higher as I go along. I'm not sure why that is. Plus, and finally, 4, 4. That's why the sort of combination method I like to use is sort of a combo of the two methods. So I like to use this right here for the coefficients here. And then what I do, of course, this right here, this is A, this is B. So here I would say x minus 3. X minus 3, x minus 3, x minus 3, x minus 3. And then these exponents, those go, well, it started off as 4, so this goes 4, 3, 2, 1, 0. So this was sort of what I had done in the Pascal's triangle method. And then this one here goes 0, then 1, then 2, then 3, then 4. And then I just figured these all out. So on my calculator, I would actually calculate what 4, 0 is. Turns out that gives me a 1. So it's 1 times x to the 4th, which is x to the 4th, times negative 3 to the power of 0, which is just 1. So that gives me just this. Plus 4, 1 is actually 4. If you do it on your calculator, you get that. If you're not sure, you can always go like this and say 4, math, probability, NCR, 1. So that's 4. So where I go, then that's just how I did this. And then I keep going. X cubed, well, that's just x cubed. Negative 3 to the power of 1 is just times negative 3. And this one right here, 4, 2. And it turns out if you've done these enough, you sort of know how these numbers go. This one here is a 6. And this is x squared. This is negative 3 squared, so that gives me positive 9. Plus this one here is 4 times x to the power of 1 times negative 3 to the power of 3. Well, this is negative 3 times negative 3, which is positive 9. And that times negative 3 again. That gives me negative 27. Remember, I have a negative base to an odd exponent, so I know my answer is going to be odd. Negative, sorry. And this one right here, then, I know it finishes with a 1 here. This is 1. X to the 0 is just a 1. And negative 3 to the power of 4, that's going to be a positive number because I have an even power. And that's going to be basically 27 times 3, which is 81. And that means then, as I do this, then I just need to sort of tidy everything up. So I have x cubed. And here I have negative 3 times 4, so that's negative 12x cubed. And this one right here, then I have 9 times 6, so that'll be 54x squared. Here I have negative 27 times 4, that would be, what's that, minus 108x. All that plus 81. So that is how you expand this one. So you can expand anything you like, any method you want. So you can either use this sort of formal binomial theorem here, or you can use Pascal's triangle method, or you can do what I like to do, use a combination of the two. I just like this because I don't like always having to do Pascal's triangle, especially if this was like a 10. That would be really complicated. But in that case, I would just go 10, 0, 10, 1, 10, 2, 10, 3, and so on. And of course I do the same. I just be careful with my exponents here and be careful how I do it. I think this is a really handy way to do really big expansions without having to do it all by hand, because this would be really long to actually write, to actually calculate what x minus 3 times x minus 3 times x minus 3 times x minus 3 is. This is what you'd have to do by hand. I'd probably break it up and do x minus 3 times x minus 3 first, figure out that thing, multiply all that times x minus 3, get an answer, and multiply all that times another x minus 3. Yuck. But that's why I would much prefer to do it this way, what we just did here. I think it's much, much quicker than doing that.